A sunrise primer. The sunrise problem, as originally described by Richard Price and Pierre-Simon Laplace, asks how one should convert analysis of the past into predictions about the future, or more specifically, how one should convert the number of past observations into certainties or probabilities about future observations. In the chapter Unknownness, we argued that big chunks of software projects are unknown, wrong, or destined to change, but we didn't say how much of each project has problems or will change. In his FSE 2016 keynote, Daniel Jackson asked, when a proof checker reports no errors found yet, how strong is the evidence? And how much more work should developers invest to get to any given degree of certainty? In this chapter, we use the sunrise equations to quantify the amounts of unknowns, changes, and errors that one should expect to see, and how one should expect those amounts to vary within projects over time. The sunrise equations are, of course, spherical cow models, yet we contend that all rational investments in software should respect the sunrise equations. First, we discuss the sunrise problem and three solutions: the original equations that Richard Price and Pierre-Simon Laplace developed, as well as a new equation inspired by Benoit Mandelbrot. Then we discuss what those equations mean. We care more about the shapes of the equations and what they portend than about the specific numbers they generate. All solutions are asymptotic, so stopping early is always necessary, yet where to stop will always remain unclear. We link the sunrise equations to classic rules of 2, 3, 6, and 12 from analysis and programming. Finally, we note that problems are often worse than the equations predict and worse than anyone admits. The sunrise problem. Techniques for reliably predicting the future remain elusive. The sunrise equations were developed more than 2 centuries ago to quantify the limits of how much can be known about the next binary event in a series. Predicting the future based on the past. The sunrise problem stems from the ancient question, what are the odds that the sun will rise tomorrow? It has come to mean estimating the probability or certainty of future observations based on the number of past observations. Specifically, what are the odds that an event will occur again, given that it has occurred n times in a row? Consider 3 events in a row. One may see the sun rise 3 days in a row, when it should rise every day. One may see a flipped coin land heads up 3 times in a row, when it should be 50-50. One may see a newbie poker player win 3 hands in a row, with beginner's luck, when he should lose most hands for a long time to come. An event that occurs 3 times in a row could come from any of these scenarios. In each case, one suspects that the event will occur again, but some doubt should remain. Consider thousands or millions of events in a row. The sun has risen every day for all of recorded history, and it still rises. The space shuttle survived falling foam problems for 18 years before exploding. The Fukushima nuclear reactors survived earthquakes and tsunamis for 40 years before melting down. In these cases, everyone agrees that events should occur again, but few guarantees exist. All of these situations suffer from hasty generalization, the law of small numbers, or the problem of induction. 3 or 1,000 or 1,000,000 positive events could begin almost any kind of series because mathematically speaking, all finite numbers are insignificant and every finite series begins an infinite number of longer series. Psychologists find that people are consistently more certain than they should be. Nate Silver notes that people often mistake luck for skill when sample sizes are small and are much more certain than they should be. So people need tools to rationally estimate the uncertainty of future events. A family of equations. The original exponential Prician equation. Richard Price's equation is f of n equals 1 minus 2 to the n to the minus 1. The probability that a binary event will happen n times is 2 to the minus n. First, assume that an event either will or won't happen, in other words, assume it is 50-50. Then apply Bayes' law recursively, because each event that does occur cuts the probability that it won't occur again in half. Price's uncertainty about the next event diminishes exponentially. We believe that Price's equation is too optimistic because it equates means and ends, the observations seen so far with the underlying phenomena, or the probability of the series seen so far with the probability of the next event. Price effectively presumes that all samples are independent and accurate, that nothing will go awry, and that new samples won't disturb the system, which are as optimistic as possible. The original linear Laplacian equation. Pierre-Simon Laplace's equation is f of n equals n divided by n plus 1, which equals 1 minus n plus 1 to the minus 1. If an event has always occurred, there should be some probability that it won't occur. So Laplace added one failure to the set of observations seen so far, the smallest discrete unit. Laplace's uncertainty about the next event diminishes iteratively or linearly. We believe that Laplace's equation is too pessimistic. The only way it could possibly add up is if the probability that the next event will succeed is always 0, which is as pessimistic as possible. We believe that adding in any other fixed probability, such as 0.5 or 0.1, is too optimistic before p to the minus 1 samples and is too pessimistic after that. One could even argue that Laplace presumed that one of the samples seen so far was wrong, or that Laplace fell for the law of averages or the gambler's fallacy. The new hyperbolic Mandelbrotian equation. Another way to view our criticisms of the original equations is that they bound the space of certainty. Price was as optimistic as possible, and Laplace was as pessimistic as possible, so the truth must lie somewhere in between. Fractal spaces lie between linear, iterative, and exponential recursive spaces. In his first published paper, Benoit Mandelbrot improved George Zipf's equation for word distribution f of s equals a times s to the minus a by using the same trick that had been used to avoid the ultraviolet catastrophe of the Weierstrass function. Mandelbrot added a constant and a scale to get the equation f of s equals a times 1 plus cs to the minus a, where a is slightly greater than 1. In the related equation, f of n equals 1 minus 1 plus n to the c to the minus 1, as long as the exponent c lies between 1.0 and about 1.6. Mandelbrot's equation lies between Price's and Laplace's equations, or more specifically, for all n greater than 0, Price's equation is greater than Mandelbrot's equation, and Mandelbrot's equation is greater than Laplace's equation. The scaling factor 4/3 is one of Mandelbrot's favorites, for which c equals log of 4 divided by log of 3, approximately 1.26186. For small numbers of observations, say less than 128, Mandelbrot's 4/3 equation approximates the geometric mean of the Prician and Laplacian equations. Smaller exponents, such as c equals 1.05, may also apply in many circumstances. We graph these equations in Figure 1 and list some values in Table 1. Notice that in a linear sense, the greatest differences lie in the range of 2 to 32 observations. In a geometric sense, they diverge forever. Notes. We cannot fault Price or Laplace for starting with simple equations because during their lifetimes computations were done by hand. Furthermore, using hyperbolic equations to describe nature only began to be appreciated nearly 200 years after their equations were first published. In the fractal geometry of nature, Benoit Mandelbrot showed that many economic and management phenomena have hyperbolic shapes. In Power Laws in Software, Pangiotis, Lourdes, and colleagues showed that many software engineering phenomena have hyperbolic shapes. So the error rates for requirements and architectures might reasonably be described by hyperbolic equations. To us, all of these equations seem off by 1 because the number of prior, quote, observations should start at 0. Saying that the table shows the nth prediction makes sense, but saying that it shows the nth observation is the historical terminology. Others, specifically programmers, have complained that the scaling constants to stretch the equations horizontally and vertically are implicit rather than explicit. Correction factors. Statisticians have developed a variety of correction factors to adjust probabilities in various ways. Frederick Basel used the inverse of Laplace's equation, 1 divided by n minus 1, as a correction factor to adjust for the, quote, degrees of freedom in the data. The inverses of all of the sunrise equations can act as variations on Basel's correction factor. Each may also need an off by 1 tweak. Asymptotes. All of the sunrise equations go to 1 asymptotically, meaning that attaining perfection would take forever. No program will ever become perfect. Hard work will eventually bring any app to within an epsilon of perfection for any epsilon that one might choose, but getting to epsilon will take a long time and a lot of effort, depending on the chosen epsilon. And analysts and programmers must stop at some point, which will leave varying amounts of potential error or change to fix later. Satisficing or stopping early is necessary. Over-investing in short-term quality annuities will waste resources, and good is the enemy of better. Because nobody can control how much is actually known about any given decision, there are no ideal times to stop, though some times may be better or worse than others. The sunrise equations are asymptotic. Iterative narrowing will eventually get your software to within an epsilon of perfection. To create a high-quality program, incrementally improve it over a long time, repeatedly inspecting and testing from independent points of view, polishing it, and narrowing the scope of change. At every step, reuse or keep unchanged or don't break whatever does work, and change or attempt to improve whatever doesn't work. Systematically polishing the code while narrowing the scope of change without adding any new functionality will systematically reduce error and improve quality over time. The trick is to narrow the scope of change to identified problems at every step or release. Iterative narrowing will eventually bring any fixed program to within any chosen epsilon of perfection. If the scope of change widens by adding new features, then quality may also worsen. Iterative narrowing applies to products as a series of upgrade projects or releases, as well as within projects as a series of iterations. NASA projects often have long lead times, sometimes as much as 10 years, which allow for many inspections and re-inspections, many tests and retests, as well as the application of many analysis tools and responses to fix any problems that are found. Reusing, or building on existing established known codes, is a key to high quality because everything that is not reused starts over from scratch, which directly increases the risk of error. Refining an existing app or prototype is often more productive than starting over because it saves all of the effort and risk involved with everything that was correct already, everything that remains the same. For this reason, we believe that reusability is the king of the ilities. All boilerplate and dead certain tasks in a project come from the requirements and architectures that got reused in many projects. Note that we ignore software rot and presume that contexts remain unchanged. Getting to epsilon can take a lot of work. The first problem with asymptotes is that getting to within any particular epsilon of perfection can take a long time and a lot of sustained effort. In Table 2, we turn the equations around and show the minimum number of observations needed to claim that any particular decision has any particular degree of perfection. Observations for requirements include initial user requests and user responses to demos. Observations for architectures include programmer requests and uses of an API or function call within an existing codebase. To get to known 95% correctness, if Mandelbrot's 4-3 equation were right, then 11 people would have to unanimously agree on every single observation. And if Mandelbrot's 1.05 equation were right, then 17 people would have to unanimously agree. To get to dead certain, or 99% correctness, one would need 39 and 80 unanimous observations, respectively. To get to 1 in 10,000 correctness, one would need 1,479 and 6,449 unanimous observations, respectively. Developing ultra-high quality software can feel like running in quicksand because everything takes a lot more observations than anybody really wants to make. Note that when we state that so many people must unanimously agree on every single observation, we mean with zero dissensions. That almost never happens, since getting 10 people to unanimously agree on anything is beyond rational hope. Also note that silently nodding one's head and voting with a majority does not equal agreement. The best way to do a lot of work is to spread it out over a long period of time. So to maximize the quality within a project, take as much time and as many resources as one can afford. NASA has long lead times and massive resources to belabor projects, 10 times as much effort per line of code, and maybe like 50 times as much as most companies when everything is considered, such as their ability to expand scope. An epsilon of error will always remain. The second problem with asymptotes is that the probability of error will never go to zero. An epsilon of error will always remain. The sunrise equations assign positive probabilities of error to the uses and reuses of requirements and codes, regardless of how old and stable they are or how much effort went into creating them. When contexts and goals are stable, then with hard work, apps will continually improve, yet apps will never become perfect, a la Zeno's paradox. Low probability issues will eventually appear. As higher probability errors are caught and fixed, lower probability errors will start to appear, but there are probably many of them, so now and again something will go wrong. When problems do not occur appreciably, then they are lurking, stalking, preparing to pounce. In Wrong, David Friedman argues that there can never be guarantees against unpleasant surprises. Just because someone got away with doing something in a given way for years or even decades doesn't mean that they got it right or that everything will be fine tomorrow. Space Shuttle example. The burnt O-rings on the Space Shuttle held for 24 flights, nearly 5 years, until one flight when they didn't. Damage from falling foam was tolerable for 112 flights, nearly 18 years, until one flight when it wasn't. Fukushima example. The Fukushima nuclear reactors worked for 40 years, surviving many earthquakes and tsunamis, until one particular earthquake and tsunami when the cores melted. Software examples. The SSL Heartbleed code appeared to work fine for 2 years until the bug was revealed by inspection. The Java binary search code seemed to work for 11 years with gazillions of calls until the bug appeared in running apps. Slow resource leaks and low probability synchronization problems may not appear until after long-running or heavy workloads. Ongoing bias. If someone failed to predict all of the errors in the first version of an app, there is no reason to believe that he or she could predict all errors in the nth version. Everyone who misunderstood the truth in previous releases probably harbors some form of bias and will continue to misunderstand the truth in similar ways. The supply of software bugs is effectively infinite. The endless security patches to commercial software apps show that improving quality is a never-ending task. Note that formal methods and model-driven development cannot change this susceptibility to error because nothing can ever leap from inductive to deductive truth. Stopping early is always necessary. Decades ago, when working on waterfall projects, our colleagues would usually finish a lot of what they had planned, useful prototypes, but bug fixes and enhancements always remained unfinished, and they would always ask for more time. Glenn Self, an executive at EDS, complained repeatedly that, quote, "There's never enough time to do it right, but always time to do it over." While we used to rankle at his observation, we have come to believe that it is both correct and necessary. All projects have limited budgets and schedules. Time and resources are bounded by one's situations and opportunities. No project has the infinite time and resources needed to write perfect software, or even the arbitrary time and resources needed to achieve arbitrary ends. Projects have only so many team members and so many hours to do useful work. So all analysts and programmers will eventually run out of time and resources and be forced to ship code with whatever level of quality they have already produced. In commercial software, windows of opportunity are limited. Most clients won't wait years for solutions, they want solutions now. First movers often gain market advantages, so commercial companies must not wait longer to ship than their competitors. The Space Shuttle had perhaps 10 to 50 times the resources per line of code as any normal commercial project, the ability to expand scope to deal with problems, and near complete control over what their trained, disciplined, cooperative astronauts would do. Yet even with all this largesse, the Space Shuttle software had bugs. Even NASA could not afford to redesign the Space Shuttle after every failed launch, and they eventually shut it down. Normal analysts and programmers who work on normal projects that don't have such large budgets will most likely make more mistakes. Many websites must deal with all of the old, incompatible browsers that Microsoft ever shipped, IE6 and IE8, and whatever crazy things that naive or malicious users decide to do, and their budgets are often minuscule. Most software projects have resources that lie somewhere between NASA and website projects. Stopping early is always necessary. The combination of limited resources with direct and opportunity costs in the presence of unknowns, changes, and errors implies that satisficing is necessary at every step of every project. Every step should make progress, but nobody can achieve perfection in a finite time, so every step must deliberately achieve lower quality than is known to be possible. This does not mean that anyone should tolerate sloppy or lazy work. Rather, they should accept that there are limits to everyone's efforts and that software could always be better. Brooks Code Example. In Chapter 15 of the Mythical Man Month from 1975, Fred Brooks wrote an example of good code that today seems seriously out of date. His code should have better names, less fussy comments, and proper unit tests. Should Fred Brooks have waited 30 more years before publishing to produce a better example? No. He wrote the best code that he could for his time and stopped early so that everyone could benefit from his example in the interim. Kent Beck, who wrote Test-Driven Development, Dustin Boswell and Trevor Foucher, who wrote The Art of Readable Code, and Robert Martin, who wrote Clean Code, describe more contemporary coding practices. They cannot help but be aware of and build on Brooks' example. Today, everyone, including Brooks, would write a much better example because we have all learned a lot since then. Animation. Brad Bird noted that scenes in animated movies, quote, can always be better. Opportunity cost. In the presence of real costs and unknowns, everyone who overinvests in short-term quality or abilities will overpay and will then lack resources to do other things later. The main reason why more does not get done is that people choose to do something else. To perfect one feature, other features must be ignored. To perfect one app, other apps must be ignored. Whenever analysts and programmers overdo one opportunity, they must neglect other opportunities, and they will pay for those missed opportunities later in other ways, which is called opportunity cost. Note that people often later rue even their best choices. Good is the enemy of better. The sunrise equations help to explain why good is the enemy of better. Eventually, everyone will run out of time and resources, and they will have to choose either to satisfice by accepting that what they have is good enough and moving on, or to strive for perfection by finding more resources to continue working. They can only do one or the other, not both at the same time. Running out of resources forces the bifurcation of hard choices. Obsession, or genius, is a key to exceptional results because it overrides any willingness to satisfy, but it is also very expensive. Nobody can control or even know what is known. Of course, everyone should get as many observations, and specifically as many prior examples, inspections, and tests as they can for each decision. But nobody can control how many times users request a given feature or how many times a body of code calls a given interface. In our experience, some problems are unique to each project. Even when many prior uses exist, analysts and programmers may not realize that they are present, or, even if they do, bother to investigate them all before making decisions. Nobody can know up front how much of a project or task is unknown or wrong or destined to change without predicting the future. Nobody can know up front which tasks will be high risk because all such judgments are subject to error. Function call example. Decades ago, we noticed that when a function that one of us had written was called only once, the odds that it would be used again without change or refactoring were low. While we never did a formal study, 50% is in the ballpark. We noticed that when a function that we had written was called from two places, the odds of reuse without change improved significantly. We concluded that every function or method should be called more than once whenever possible. Even so, most of our functions still get called just once. When to stop always remains unclear. The need to stop early suggests that there must be some concept of good enough for now, because otherwise nobody would ever finish working on anything. But the sunrise equations don't actually say what good enough for now means. Nobody can know how many steps to take in any given situation without knowing what is gained by the additional steps, which cannot be known without predicting the future. We believe that there are no perfect times to stop, though there are often better or worse times. One good place to stop is just after fixing all important known problems, though of course one may misjudge what is important and nobody knows what unknown problems will arise. Another good place to stop is after investing a specific amount of effort, as suggested by the rules of 2, 3, 6, and 12 listed below. Analysts and programmers have lots of practical experience with good enough for now. Software projects are full of arbitrary short-term deadlines for tasks, iterations, and projects. We have seen many occasions when managers let their people, quote, play with difficult problems for days or weeks, and then on some seemingly random day demanded, finish now. Everyone ships what they have after running out of resources. These approaches to good enough for now are ad hoc and possibly even random, yet they embody reasonable heuristics. Aware rather than oblivious. Appreciating that all analysts and programmers must satisfy on every task may help to make the arbitrariness of these decisions a bit more overt and honest. Caveat. Note that good enough for now differs completely from good enough for later. The Space Shuttle and Java binary search both worked fine for a while, but not forever. Good enough for now in requirement and software engineering. How good should requirements and source codes be before moving on? When should one cut off near-term investments? How good is good enough for now for one step forward in a project? Mike Hinchy noted that there will always be a tension between cost and reliability, though he didn't define the link. Various rules of 2, 3, 6, and 12 recommend investing corresponding amounts of effort. Empirically, for most software projects, good enough for now means 6 to 12 observations for analysts and 2 to 3 observations for programmers. The spectrum of number of observations. The spectrum of the number of observations is vast. Each different number of observations embodies a different trade-off of cost versus quality. One observation for custom and innovative work. A lot of custom and demo software is based on one observation and gets developed just once. Consulting. Consultants tailor a lot of software to individual clients and integrate seemingly random data sources in one-off projects. Consider writing a custom report for a VIP or piping yet another random feed into a database. Innovation. True innovation means that there is no prior art. New software products have little prior information to base decisions on, except maybe, hopefully, one visionary opinion. When one user asks for a new feature based on the Mandelbrotian equations, the results are probably around 50% correct. The results of one-off decisions and tasks resemble pure luck. 2 observations for commercial code. Reviews. We have seen many commercial projects require that all code be paired on or inspected at least once before commits. Based on the Mandelbrotian equations, these commits are around 67 to 71% correct. 3 observations for high-quality code. Refactoring. The number 3 looms large in the lore of refactoring. Martin Fowler quotes Don Roberts writing, quote, "The first time you do something, you just do it. The second time you do something similar, you wince at the duplication, but you do the duplicate thing anyway. The third time you do something similar, you refactor. It takes 3 observations to make good decisions about structuring code. If anyone could reliably design an architecture correctly the first time, they wouldn't need to refactor." Reuse. The number 3 looms large in the lore of reuse. Will Trace quotes Ted Biggerstaff writing, "Before you can develop reusable software, you need to have developed it 3 times. If anyone could predict how a chunk of code would be reused before then, they wouldn't need to keep redeveloping it." Understanding. Bob Balance stated that you understand a problem when you know 3 solutions to it as well as 3 reasons why each solution is wrong. Reviews. In Making Software, Dwayne Perry describes a large embedded project where all code was reviewed by at least 3 peers. The Mandelbrotian equations imply that decisions based on 3 observations are probably around 76% to 80% correct. Decisions based on 3 observations are enough better than pure luck to allow developers to meaningfully proceed, but remain far from certain. 6 observations for commercial analysis. Analysts have adopted various rules of 6 for requirements. Interviews. Alan Cooper and colleagues encourage designers to interview 4 to 6 users for each role. Analysis. Carl Wiegers notes that large groups of analysts may be too unwieldy to make effective progress, and in Too Many Cooks suggests that 6 may be a good upper limit on the size of a group. When 6 users or analysts ask for a new feature like, quote, "I need autocompletion in field F," what does anyone really know? The Mandelbrot equations suggest that analyses based on 6 opinions are around 87 to 91% correct. These decisions are still semi-known and far from certain, yet everyone can proceed with a fair amount of confidence. 12 observations for high-quality analysis. Analysis. We've heard that NASA projects often have teams of about 12 analysts. We have seen teams of about 12 analysts and programmers work on various healthcare projects. Reviews. We've heard that a number of companies have architectural review boards with 12 or so members to verify conformance to standards. In Making Software, Perry notes that on his large embedded project, architectural decisions were reviewed by teams of up to 15 peers. If each requirement or architectural decision gets 12 observations, then Mandelbrot's equations suggest that around 92 to 95% of such decisions will endure. These decisions remain uncertain, yet analysts and programmers can proceed with a lot of confidence. 24 or more observations. We can imagine rules of 24. Analysis teams would have 24 or so members. Code would get inspected by 24 peers. If the Mandelbrot equations describe software, then such requirements and codes would be 96 to 98% correct. Michael Lewis noted that, from a frequentist point of view, it would take a sample size of 130 to get a 90% chance of generalizing to society or to the whole world. Sweetspots and Tradeoffs. Sweetspots. The many rules of 2, 3, 6, and 12 in analysis and design embody important heuristics that define good enough for now in the face of unknowns, uncertainties, and errors for most projects. Newer or less critical work. By inspection, 6 observations for analysts and 2 observations for programmers is the heuristic sweet spot of certainty for most requirements and source codes in younger and less critical programs. Mature or more critical work. By inspection, 12 observations for analysts and 3 observations for programmers is the heuristic sweet spot of certainty for most requirements and source codes for maturer and more critical programs. Trade-offs. Roughly speaking, doubling the cost halves the remaining error rate and vice versa. Getting fewer observation increases risk and reduces cost. Getting more observation increases costs and reduces risk. One can find incrementally better answers, but only if one spends significantly more time and energy. Larger numbers of observations can be effective when applications are more stable, when lots of stakeholders are well versed in the issues at hand, and when high quality matters more. Getting more observation also provides more political cover when problems arise. So why not insist on 24 or 130 observations for every requirement and design decision? Because no organizations can afford to do so. Getting more observations becomes increasingly more expensive with diminishing benefits. Additionally, Fred Brooks noted that interactions grow with the square of the number of people in a group, which limits the effectiveness of large groups. Projects that have the time and resources to get lots of real observations should go for it. But in the meantime, progress on other features and programs will remain blocked. 6 to 12 observations is the point of diminishing returns, even for NASA. Diminishing returns. Take only one step at a time. Every task or iteration embodies one step forward in a project at some scale. The Sunrise equations show how much quality can be achieved by each step in general terms. Every step should only attempt one step's worth of effort, and each step can only achieve one step's worth of results. Nobody can do more. Nobody can eat an elephant in one requirement or boil the ocean in one line of code. Take reasonable steps forward, but no more. For the sakes of productivity, efficiency, and consistency, one should take as many steps forward as one reasonably can afford, but do no more because additional steps become increasingly less effective. Due to diminishing returns, taking multiple steps leads to higher quality through disproportionately higher costs. Noticeable improvements may simply be too expensive. Harder to build bigger consensuses. Keith Sawyer notes that greater diversity tends to inspire greater creativity as long as groups build effective consensuses. But building consensuses is harder in larger groups. Whenever a group fails to build a consensus, then its diversity will be wasted, a la Uyghur's Too Many Cooks. Oversized groups will have more debaters and head nodders who will obstruct or mislead progress. Overinvesting wastes resources. Everyone knows that greater efforts can produce better results. Analysts and programmers often aspire to higher standards of quality, which would surely be possible with more time and resources. But when returns diminish, then striving for additional quality will primarily waste resources. The conflicts between the quality benefits of more steps and the productivity benefits of fewer steps suggest that everyone should start with a modest number of steps and incrementally add effort later. When multiple observations help. Note that multiple observations help most when the probability of getting each decision right is better than 50-50, but not by much. We believe that lots of RE and SE decisions lie in these middle ranges. In Table 3, the group success rates are the geometric mean of the individual success rates. When the odds of success are less than 50%, getting one observation is the best choice because adding more observations and voting will actually make decisions worse. When the odds of success are high, say more than 90%, then getting more inputs doesn't really help. So teams and multiple observations help most when the odds of making a good choice are in the 55 to 85% range. Worse than the equations predict, worse than anyone admits. For many reasons, the error and reuse rates of all requirements and architectures are worse than the Sunrise equations predict. Behavioral economics, empirical software engineering research, and practical experience suggest that requirements and architectures are worse than anyone admits. Lots of software decisions are hard. Ambiguity. Everybody wants easy to use, but that can mean opposite things for power users and newbies. Does it mean fewer confusing details and fewer shortcuts, or fewer steps and more shortcuts? Does it mean put together all of the controls that affect a decision, which can be overwhelming to newbies, or put less commonly used controls into preferences or templates, which are harder to find and more annoying for power users? Or should it be configurable, which potentially adds detail for everyone? Consider good error checking. Reconfirming every input with a pop-up dialog is annoying and leads to habituation errors. Reconfirming no inputs turns every action into a potential typo or clicko. Exactly where should one draw the line, and what does one do to accommodate both power users and newbies? These questions have few easy answers, and the odds that any specific choice is correct might be poor. Irrationality and inarticulation. As we point out in the chapter Unknownness, users, analysts, and programmers are all irrational, or crazy. More often than anyone admits, users either do not know the truth, or, when they do know, cannot articulate it. Psychological anchoring affects everyone. Perhaps recent water cooler discussions with colleagues influenced user opinions. Perhaps designers asked leading questions. People can make mistakes, such as misspeaking, when stressing, multitasking, or rushing. So when interviewees or analysts are under stress from a boss or a spouse, their answers will be wronger. Near deadlines, decisions will be wronger. The IKEA and NIH effects occur when users argue for their own mediocre ideas rather than the better ideas of their peers and rivals. If users are 90% rational and accurate when expressing their own needs, which we believe is insanely optimistic, then the odds of error will move at least 10% closer to 50-50. The real odds are probably much worse. Biased sampling. Participants in the inquiry process may or may not represent the true user base. Maybe the interviewees know exactly what they need. Maybe they could be spared from other tasks or have pull to get out of meetings. Maybe they are power users who have very different needs than the true newbie user base, or vice versa, and their opinions are biased inappropriately. As a rule, designers want to interview users with above average expertise who will probably better understand and articulate their needs, but this also makes them less representative. Analysts and programmers often make decisions based on their own opinions and experiences, even though they are not representative users either. Social and political behavior. Social and political behaviors can increase speculation by users and analysts. A user may want to please a colleague or manager by forwarding a suggestion that otherwise he or she considers unimportant. How many of your friends have ever asked you to like a cause or a project that you know nothing about? A busy user may say and believe, so and so can speak for me, even though the proxy says all the wrong things. A designer may focus too narrowly on friends and favorite users and omit important functionality. A designer may try to please too many users and add in too much confusing flexibility. The politics that decides who participates in the requirement process may affect the outcome more than any individual. Fatigue. Decision fatigue occurs whenever anyone makes many decisions and eventually gets tired and starts saying, whatever. All decisions after that are effectively random. Inconsistent input. In many cases, analysts and programmers get bug bases full of complaints, but complaints are much less meaningful than deliberate decisions about what to do. Inconsistent coverage. Most software projects entail many decisions, and no project ever gets 3 opinions for every single decision. Newer projects are worse. Many requirements and architectures have gaping holes and do wrong things deliberately in well-intended but naive ways. One can implement awkward or useless features and clumsy architectures that have no coding bugs, and one can write useful features that have significant bugs in corner cases. This resembles the difference between sample errors and model errors in statistics. Duane Perry notes that source codes are not the biggest problems for successful projects, rather the requirements and architectures are. He discusses, quote, the lack of precision and completeness in requirements and design documentation. Requirements. In our experience, new requirements are horrible. They are continually revised in every project that we have ever seen. During development, almost all requirements must be clarified or explained, and many get changed to fix ambiguities or omissions, though sometimes they are rewritten from scratch. Many calls to user helplines implicitly criticize clumsy GUIs and features. In other words, implicitly criticize the requirements. Architectures. In our experience, new software architectures are horrible. Architectures are expected to endure, so architects must predict the future. As they endure, architectures accrete cruft and work less and less well, and they can't be fixed due to the need for backward compatibility. All glue code, workarounds, and versionings implicitly criticize architectures. Larger projects are worse. As apps get larger, the odds that individual requirements or APIs are correct decrease. Contextual complexity. A feature in isolation may be easy to find and obvious to use. The same feature in the context of a complicated app can be hard to find and confusing to use just because there are so many other distracting details to wade through. Users cannot use features that they cannot find and figure out. Users struggling with a large, unfamiliar app may not know where to look for a particular feature and may give up. Names and labels are often confusing in large programs due to context. Tech support workers field many questions that are supposedly obvious in the GUI or in the manual. We know of cases where magazine reviewers claimed that important features were missing from major commercial apps when the developers had spent a lot of time implementing those features, even doing usability studies. Presumably, the reviewers were savvy users who either did not find what they were looking for or did not appreciate what they did find. Cross-cutting effects. When many analysts work together, some details will cross boundaries of responsibility. What seemed like an unimportant detail to each may coalesce into an important requirement for all analysts together. For example, when each dialogue is designed by a different person, the flow from one dialogue to the next may be inconsistent. Error handling is also hard to do consistently. Aspects can capture small cross-cutting requirements by combining them into fewer, larger issues if analysts can perceive them as such. These issues are often handled by style guides or standards and are treated as errors when wrong, but we believe they should be treated more positively as explicit aspects. Architects deal with fewer irrational users directly, so their decisions may seem safer, but architects have their own problems. Architectural decisions are often expected to endure a long time and often affect many parts of an app, so architects must predict further into the future. The conventions and standards that architects use can interfere with effective decisions in novel situations. Also, expectations are higher, and architects probably need stronger egos to survive, which likely increases overconfidence and stubbornness. Worse than anyone admits. Disagreement. The sunrise equations only apply when all users agree unanimously about decisions. When users disagree about decisions, then the odds that a decision is right quickly move toward 50-50. Consider two users who want better search and another user who would rather have better reports. Consider two architects who want to move apps to the cloud and browsers and another architect who wants to stay with client-server and classic GUIs. Negotiating a unanimous decision may neither change the underlying opinions nor improve the odds of being right. People often merely hold their tongues and nod their heads silently in the presence of others with more authority. Users can disagree about the most important things, such as what an app should do, and agree about the most trivial things, such as using the corporate logo and color scheme. Just because users appear to agree doesn't mean they are right. Just because users appear to disagree doesn't mean that the issue is unimportant or that a good answer cannot be found. Agreement per se should not be used to make decisions or set priorities. Uncertainty. Getting many inputs from many different users doesn't guarantee useful opinions or insights. Many users don't have an opinion and don't even want one because they are busy with their own problems. Sometimes users want things that are impossible. For example, they may want web pages to change the appearance of the browser icons in the taskbar. Getting a large number of code reviews from peers doesn't guarantee that anyone will say anything useful. In all of these cases, people may agree that there is a problem, but not on how to solve it. Ease. Alan Cooper and colleagues encouraged analysts to strive for 6 opinions from real users. Getting more than one opinion from an analyst or programmer grounds the process in reality. Cooper and colleagues also state that during analysis, later interviews should fill in missing details rather than reconfirm known information, which lowers the number of effective observations. They also throw away all but the top one or two resulting personas, which lowers the number of effective observations again. We will oversimplify Cooper's process and give them the benefit of the doubt and say that on average, they base each design decision or requirement on 2 or 3 user observations. Omissions. Like nulls in databases, omitted opinions in user surveys are tricky. An omission could mean anything from I agree, I believe that others have made my point, to I abstain, I don't have a useful opinion or it does not apply, to unknown, I forgot to state my opinion, to I disagree, I didn't mention it because I want something else entirely. Presuming that users who say nothing intend to abstain is absurd. Perhaps each omission should be treated as a 50-50, which will not change the decision, but will lower the certainty. Notes. Binary events. The sunrise problem describes the probabilities of binary events, like flipping coins. In software, whether a feature or function will have bugs and whether individual requirements and architectural decisions will remain unchanged are also binary events. Unfair comparison 1. Comparing the Space Shuttle and the Fukushima reactors to Java binary search is problematic, even though they all concern errors. There were significant differences in complexity, quality control, and consequences. Richard Feynman showed that known Space Shuttle errors were left unfixed. We don't know whether the Fukushima operators ignored known problems. The binary search bug was not left unfixed for long, but probably many other Java bugs were. Unfair comparisons 2. Comparing analysis and programming is unfair. Programmers have tools that analysts lack, like linters and type checkers, that catch many errors. Appropriate. One difficulty with applying the sunrise problem to RE and SE is whether it is appropriate at all. In many situations, one knows a lot more about an event than the number of times it occurred in the past. For example, we know from other scientific models that in about 4 billion years the sun will explode, and around that time the odds that the sun will rise will steadily decrease until one day they will become zero. But for all of the sunrise equations, the odds will steadily increase until the day the sun explodes. On that last day, the estimates given by all of the sunrise equations will be horribly wrong. Testing, budgeting, and scheduling have similar problems with predicting the future and can also use the sunrise equations, though we leave the elaborations of those topics as exercises for readers. We are unaware of any other descriptions of the hyperbolic solution to the sunrise problem. We hope that astute readers will point out appropriate prior work. Pronunciation. One drawback to the Mandelbrotian equation is that the pronunciation remains unclear. We fear that debates over whether Mandelbrotian rhymes with ocean or OTN could fracture civil society in software engineering. We also fear that some may stubbornly cling to the wrong answer. We will. The sunrise equations are used in the next chapter, Polish versus Rot. Laplace used the term rule of succession instead of the term sunrise problem. Another Laplacian equation. Another Laplacian equation, x prime plus 1 divided by n plus 2, adds one success and one failure to each set of observations. It moves the estimate toward 50-50 rather than toward 0. Other rules of 3. For many years, we, the authors, have tried to find 3 examples of each point in our essays. It takes 3 licks to get to the center of a Tootsie Pop. The sunrise equations put numbers on the sampling problem. Frequentists tend to believe that low probability events, like winning the lottery or unknown bugs, don't occur. The sunrise equations are Bayesian because low probability events will occur eventually.